This video is going to be on the effect of intermolecular forces on vapor pressure and boiling point. It is critical that before watching this video, you watch the videos in the next sections on intermolecular forces. Otherwise, you're really not going to understand this. We're going to predict which compound has a higher vapor pressure and a higher boiling temperature or lower. And so the three forces that we've talked about in the next section's videos are London, dipole, and hydrogen bonding. London are weak, but they're in everything, and there can be a lot of them. Dipole are strong forces, and H bonding are very strong. Let's draw a graph. You've seen this graph before. It's vapor pressure versus temperature. And if I take a compound, any compound, and I have it at a very low temperature, for example, 0 in water, we have very low vapor pressure. And as I increase the temperature, the pressure, the molecules start moving faster, kinetic molecular theory, and the pressure in our piston starts to increase. If I get to 1 atmosphere, 760 millimeters of mercury, I have boiling occur. And for water, this would be at 100 degrees. This is a typical vapor pressure curve. Water has very strong intermolecular forces as things go. If I do a different compound, one with weaker intermolecular forces, the vapor pressure is a lot higher at 0 degrees. It starts out higher and it goes up. It's the same kind of curve, and it will go until it reaches 1 atmosphere, atmospheric pressure, and then boiling would occur at this temperature. So this curve has a higher vapor pressure point for point at each of these temperatures. It has a higher vapor pressure than water, and it is boils at a lower temperature. The water has, this one is water, H2O, and we'll call this one methanol. We'll talk about those first. Methanol has weaker intermolecular forces. Water has stronger, has lower vapor pressure. It's always down here, lower vapor pressure, and a higher boiling temperature. That's the take-home point. Now, all you have to do to predict these is look at which has the stronger intermolecular forces. So I'm going to draw two compounds out here. Here are the two compounds. This one is going to be called propane, and this one is butane. So here's the two structures of these, propane and butane. Down here's butane. It's also sometimes written like that, which we'll talk about later in the semester. This is a condensed structural formula here, where each CH3 is bonded to a CH2, like over here. And so we have a CH2, CH2, and a CH3, and a CH3. You'll see this on the exam, written like this. Well, same compound. So what are the intermolecular forces for propane and butane? Well, there are no dipole because there's no polar parts of these. And so the only thing they have are London forces. And this one's going to be smaller intermolecular forces because it's a smaller molecule. Remember, the larger the molecule, the greater the London forces. So we expect propane, which is the smaller, to have the higher P-vape and the lower boiling temperature. And butane will have the lower P-vape and the higher boiling temperature. And that's exactly what we find. So that's all there is to this. We'll compare a couple others here. I'm making a couple of them. So here's the first set, CH3, CH2Cl, and CH3, CH2H. And so the forces they have, we know what they are. This one is going to have London and dipole. I'm just going to call it dipole forces. So it'll have those two. This one will have London only. The London are about the same because these are about the same size, and so this has dipole included, and that is going to increase the intermolecular forces of this one. And so we expect CH3, CH2, Cl to have stronger intermolecular forces, lower P vape, and increased boiling temperature. And that's what we find. Let's do another one. So here's my the next two compounds. They're called isomers. They both have the same formula, C4H10 and C4H10, but this is a straight line molecule, and this one is one that has some crooks and crannies on it because it has this branching. It's called branching. Here's what they look like if I draw the Lewis dot structures. Okay, and so the question is, which has the larger intermolecular forces? They only have London, but this one's branched, so this will have less London. This one's London. And so this one will have the greater intermolecular forces because it's linear. It does not branch. Okay, so this one here will have the lower vapor pressure. P vape is low, and T boiling is going to be higher than the compound down here. This compound is going to have a higher vapor pressure. P vape is high, so the boiling temperature is low. We'll do one more. So I've got two sets of compounds, and I want to know which has the higher boiling point. So the one with the higher boiling point will be the one that has a stronger intermolecular forces. So the forces on each of these, HBr and HCl, both have London and dipole. They're about the same, dipole, and so HBr, if you look on your periodic table, is a larger molecule than HCl because we're going down the periodic table, and so HPr will have the higher boiling point and a lower vapor pressure. Now when we do this one, HF or HCl, we note that they have London. They both have dipole, and so you might think that HCl, since it's bigger, has a stronger intermolecular forces, but HF has hydrogen bonding. So HF has H bonding, and HCl does not. Therefore, HF has the stronger intermolecular forces, so that HF will have the higher boiling point. T boiling point is high, and P vape is low. And I better write it down up here in case I misspoke. In this one, HBr has the stronger intermolecular forces, so T boiling is high and P vape is low relative to each other. That's all there is to it. Okay? Do the homework.